should put in your attendances first. Okay, I see 20 people are here, so it should be okay. You can start. All right, to begin with, let me try to shed some light on yesterday's confusion regarding this inversion. So when we tried to go from Lagrangian to Hamiltonian, so we were trying to go from Lagrangian to Hamiltonian via Legendre transformation. And I told you that at the first stage you should try to invert your velocity. This is generalized velocity. This qk dot should be a function of other pi and qy. Okay. Now there is an implicit assumption that this can be done. So the implicit assumption is that so this can be done. Okay. If it cannot be done, then you cannot go from Lagrangian to Hamiltonian via Legendre transformation. Okay, there are sophisticated techniques that perhaps is not suitable for this class, but you will encounter an example of this category. Is that so? What you will do if you cannot invert like this? You can just say that via Legendre transformation we cannot find the Hamiltonian. In fact, I don't know how many of you will later take on quantum field theory. So in quantum field theory, when you quantize the photon field, so these are, if you do not understand this at this point, it's fine. Okay. So quantization of photon field, then you will see that the generalized momentum will turn out to be 0. Okay, and we have to take special care to go to the Hamiltonian formalism when we quantize this photon field. So this is just a side note that you can remember that if you want an example that when is there a physics example where we cannot have this inversion relation, then that example, one of the example is here. Okay, when you learn about quantum field theory. So that is a small comment. So yesterday, after the confusion, I consulted some people who were at the same business, and from what I gathered is this should be the answer. So I hope things are a bit clear now. And if there are any other question from yesterday's class, I can take it now, or I will move on.
Sir?
Yes.
So there is this homework in your notes in which we have to find the normal coordinates. Sir, can you please discuss this, because in that x1 and x3 relations are basically the same, because their relations are coming same. So I'm unable to
Which homework you are referring to in the at the end of normal coordinates?
Yes, sir. In your notes, sir.
So I calculated the normal coordinates first of all. Then I asked to recalculate it using the standard procedure. Is that so?
No, sir. Sir, in this, you have given us V2, that is our A12, A22, A32 is equal to 92, N2, and 101.
Okay.
Yes. So in this, I am unable to find any relation, because in the matrix of the A matrix, so the first row and the third row are basically the same. So
first row and the third row is basically the same.
Yes, sir.
And then
In one
yeah,
and two and three.
but you have to first of all, so this you have to first of all find the n1, n2, and n3 via the normalization I mentioned earlier. That so you need to satisfy this a1 omega square, sorry, a1 transpose m a1 equals delta ab, something like that. Did you check that those are satisfied?
No, sir. Actually, I checked
So yeah,
this.
so I perhaps I asked you to do using that procedure. Okay,
Okay,
but
sir.
anyway, even if this A matrix, yeah. So I see the homework now. The elements of A are identified as A K alpha. Now normalize A to find A bar. Okay. So first you find this A bars according to the normalization condition. Uh, so you have to fix N1, N2, N3.
Yes, sir.
Okay, and then you can invert the matrix. Let me see. What you were saying is that you cannot invert the matrix because the determinant is coming to be zero, something like
Yes,
that.
sir. Sir, determinant is coming zero, sir, because in the center there is this zero in n1, n2, and three, and then again in the third row there is n1, n2, and three. So
But you see the determinant of A should not matter. What you need to invert perhaps is, let me check. Let me check. Well, I haven't done it. Uh, okay, first you calculate A bar, then you check if the determinant is still zero. Okay, so you find A bar according to the relation this A bar transpose M A bar equals 1 according to that. Okay. Then perhaps you find it.
A bar is like normalized.
Normalized version of those A. N1, N2, N3 will be fixed by that.
Okay.
Okay. So N1, N2, N3 will no longer be arbitrary. It will be fixed by those relations. Okay. And then you
Okay.
proceed to find. Hopefully it will work. I do not see any reason why it should not work. Okay.
I'll try.
Uh,
Okay.
all right. So you try and then uh, and perhaps I might have also made a mistake in that in writing x2. Yeah, perhaps I have made a mistake in writing v2 there. It should be n2 times 1 0 minus 1.
Yes, sir. That's actually what I was saying. Because unless and until, sir, there is like, because there are three variables and only two equations, then so it is impossible to establish xi
Yeah,
one,
yeah.
xi two.
So yeah, please correct that, and then yeah, I will make a correction also. Perhaps that yeah, yeah. I have copied it wrong then. Okay, yeah. So from that, yeah, it should be n2 1 0 minus 1. Okay. Thanks. Then I have to correct that.
Yes. Thank you, sir.
Okay. All right. Any other questions? Okay then. So let me proceed to some some discussions about the phase space. So the first example I will take on is the 1D simple harmonic oscillator. So I will denote the generalized coordinate and momenta by P and Q respectively. And if you find the Hamiltonian from the Lagrangian, the structure of the Hamiltonian will turn out to be this P square over twice M. plus of m omega square q square. So this is my Hamiltonian for the one-dimensional simple harmonic oscillator. Okay. So there should be in from this exercise you will understand something very important, which in my mind is very important. So before I proceed, tell me if you know two aspects of one is from quantum mechanics, another is from statistical mechanics. So the aspect number one is that do you know that the harmonic oscillator is the minimum uncertainty wave packet and the uncertainty is h cross by 2? Okay, so this is the minimum uncertainty. Okay, and harmonic oscillator is the example of this. The wave function of harmonic oscillator leads us to the minimum uncertainty. Do you know that? And from quantum mechanics, do you know this thing?
Yes, sir.
All right, very good.
So it is
So this
valid
is
for ground state.
yes. I mean, this is the property of the Gaussian wave packet, and in the ground state Gaussian wave packet, it's h cross by 2. This is the minimum uncertainty. You cannot go less than that. Okay.
Yes, sir.
Yeah. Any other system, the uncertainty would be greater than h cross by 2. All right. And in statistical mechanics, when you try to figure out phase space, right? So the phase space is also delta p delta q, the minimum volume in one-dimensional phase space. So then it tells you that the minimum volume in phase space, that is equals h. Okay, it's not h cross by 2. That is h. Do you know this also in quantum statistics? So
Yes.
yeah. So now, have you ever wondered how these two connect? Like, why this thing is not h cross or h cross by 2? Because the minimum uncertainty can go. So here actually you are writing delta p delta x equals h cross by 2, and here you are writing h. Have you wondered why, or did this question occur to you? Or maybe, do you even know the answer? Okay, anyone with any guesses?
So maybe due to the dimensionality of the phase space, if we are in general talking about three individual components of space and three of momentum.
No, I am talking about the simple, just one-dimensional phase. I mean, two-dimensional phase space, just p and q. So here you have p, here you have q, here you have p, and the smallest volume you can consider, that is basically the area, is h. And if you go to three dimension or 6 dimension, it will be h cube, because h for every dimension. All right then. So perhaps you will get an answer that how these two things connect in this exercise. Okay, so you will get an idea of how things evolve here. All right, so first of all, let me give you an example how to deal with Hamilton's equation. So you have two equations. So first of all is q dot equals del h del p, which is again the definition of momentum, and the second one would be uh, uh, p dot equals minus del h del q, and it should be minus m omega square q. Okay, so usually So when you deal with Hamilton's equation, remember the structure usually would be this. So in the first equation, q dot will be related to, what am I doing? So in the first equation, q dot will be related to p, and in the second equation, p dot will be related to q. Okay. Now this is kind of a nested equation, and that's why you basically take the derivative of one of the equations and replace the dot from the other equation. Okay, so this is a standard trick, and it would be valid across many of your examples that you encountered in your problem solving set. So whenever you see that q dot is related to p and p dot is related to q, the standard trick is that you take the derivative of any of the equations. Let's say this one, I take another derivative, so that will give me q double dot equals p dot over m, and I can now substitute p dot from, sorry, this one. So if I do that, then I get the equation q double dot plus omega square q equals 0, which is the same as the Lagrange's equation. Remember, if you instead of using Hamilton's formalism, if you obtain the equation of motion from Lagrange's equation, you would have directly get this equation. So q double dot equals omega square q equals 0. And the no surprise is that if you actually solve this equation, it would be an oscillatory solution. So I can write the solution as, so q as a function of time, you can write it as a, let's say, cosine omega t plus delta. Okay, so this is a second order differential equation. So there would be two constants flying over. So one is a, that I call the amplitude, and the second constant is delta, which is the phase. So this has to do with the initial condition of the simple harmonic oscillator. It means that from where the simple harmonic oscillator start and what is the phase like of that oscillator at t equals 0. So if you specify that, then you basically get a and delta, and that fixes your motion completely. Anyway, so let me, for completeness, write down, this is my amplitude and this is your phase. All right. Now now for the solution of p is basically you can obtain from here. So p is m times q dot. So what you can write, p is m times q dot, and you can write it as minus m a omega sine omega t plus delta. That's your p. Now, just for fun, if I look at my Hamiltonian, so Hamiltonian, remember, was a function of q and t. Okay, so Hamiltonian is a function of, sorry, p and q. So Hamiltonian is a function of p, which is an implicit function of t, and that is basically, let me write down, so p t square by twice m plus half m omega square qt square. All right, so from this I get the impression that Hamiltonian might depend on time, but I know from my earlier lessons that if my Lagrangian or the Hamiltonian does not explicitly depend on time, then the total Hamiltonian will not be dependent on time also. So let us check explicitly. If I substitute my p and q here, so if you substitute p here and q here, so you can check that the sine square plus cosine square will be 1, and both of them gives you half m omega square a square. So thing will be half m omega square a square. Give me one moment. Okay, so sorry about that. Anyways, so this should be your total energy, and this matches with our expectation that we know that half m omega square a square is our total energy for a harmonic oscillator. So for future reference, I will call this thing as E, and I will remember that E is a constant. All right. So although my total energy is a constant, I know that my P and Q can depend on time. So, and the time dependence is captured by this oscillatory nature. So if I try to draw my phase space diagram, this is one of the standard practice to draw phase space diagram for several systems. So you should be practicing these things. Okay. So let me draw the axis. Now, suppose in this direction I have my QT, and in this direction you have your PT, right? So remember, P is a simple harmonic motion along the vertical direction, and Q is a simple harmonic motion along the horizontal direction, because you see the solution of P and Q. So Q is a simple harmonic oscillation. P is also a simple harmonic oscillation with a different amplitude, of course. Okay, the amplitude of Q and P are different. Okay, so so Q is a simple harmonic oscillation along this direction, and P is along this direction with amplitude, with a different amplitude. So when two different simple harmonic oscillation superimpose in a perpendicular direction with a different amplitude, you get an ellipse, which can be directly seen from the equation also. If you notice that you have a equation of the form p square by twice m plus half m omega square q square equals E. So if you recast it in this way, so that implies perhaps q square by square root of E by 2 sorry 2E probably. So 2E by m omega square, this thing's whole square, plus p square by square root of 2me, this is whole square, equals 1. Okay, so this is the equation of an ellipse, and you know the major axis and minor axis uh, to be A and B. So suppose this thing I called my A, and this is my minor axis to be my B. So if I draw the ellipse, I don't know how nicely I can draw. Okay, it's nice enough. So the thing is, since my energy is constant, so the if the system was initially at one of these points, it will move along this ellipse. Okay, either clockwise or in the anti-clockwise direction, depending on the initial condition, but it will move along those ellipses. Now, so I know that this is my A, and this is my B, and the area of the ellipse in phase space. So if so this is one ellipse for energy E, let's say, because remember my major axis and minor axis depends on the value of my energy. Okay. So the area of the ellipse, which I call the volume of the ellipse, of course, in general these are phase space volumes. So let me call the volume of the ellipse, that I will denote by V, the volume in phase space, and that should be given by pi times A times V. So that is the formula for the area of the ellipse. If you do the computation, so pi times square root of 2e by m omega square times 2me, it should turn out to be pi times 2e by omega. I am not wrong. Yeah, pi times 2e by omega. So I noticed that this volume that the volume of the ellipse actually depends on the energy. So it is a function of the energy of the system, which is a constant. So the harmonic oscillator with a certain amplitude or a certain energy will trace out an ellipse of a certain volume. Okay. Now let us come to the quantum picture. So in the quantum picture, uh, basically the energy levels of the harmonic oscillator, one dimensional harmonic oscillator, are definitely quantized, and their energy levels are denoted by En, where of course n runs from 0 to infinity if you choose so, and En is given by I guess n plus half h cross omega. Okay, so uh, now every En basically traces out an ellipse. Okay, so the space between, so the volume between two consecutive quantum energy levels. So what I change that, the volume in, so let me write phase space volume in between two consecutive, I am not sure if I'm writing this spelling correctly, energy levels, that should be given by, say, between n plus 1th level minus nth level. So what I am interested in finding, suppose this is my En. Yes, this is my nth energy level. Okay, this orange one.
Hello.
Now, yes,
Sir, I have a question.
yeah.
Regarding the quantum picture, how can I draw the ellipse?
What do you mean? How can you draw the ellipse?
Sir, if in a specific point the P and Q are determined with infinite precision.
Yes, I'm not saying that it is determined by infinite precision. And that's the phase space uncertainty you are talking about. So you do
Yes,
not
sir.
know whether the particle is in between. A particle can be either here or here. Okay, I am not saying that P and Q are determined with infinite precision. I am saying that whatever be the P and Q, the system should lie on this thing. So you know the energy with infinite precision, because those are energy eigenstates.
Yes, sir. Yes, sir.
So the system can lie anywhere on this ellipse. So in the phase space, the system can lie anywhere on here. So that is the thing you know. You do not know P and Q.
No, sir. In any point, if I in on that point P and Q have a specific value, that then
I am not saying that the system is on this point. I'm just saying the system is can lie anywhere within this.
sir, I am getting the point, but The ellipse should be fuzzy type.
No, the ellipse should not be fuzzy because a certain ellipse denotes a certain energy, and you know the energy with infinite precision.
I'm not able to understand how can I draw the ellipse. In fact, in that phase space point plane, if I in a certain point the P and Q have a certain value, then to draw the entire ellipse, I have to know this point out.
Of course, you know the ellipse. I mean, you know, because the quantum picture does not spoil your determination of energy. So even if you calculate the energy eigenvalue in that thing, so that is the energy eigenvalue. You know that as in a very precise manner. So
Yes.
your quantum mechanical Hamiltonian is say p square over twice m plus half m omega square q square. Suppose you are in the nth quantum state. So I'm just saying that h on n gives you En on n. Now,
Yes.
what you might be confused about, you have to find out the expectation value of kinetic energy and potential energy in that state. And if you do that, you basically get half of the Tn. So if you basically calculate the expectation value of kinetic energy, this is a standard exercise, that should come out to be En by 2. And the expectation value of potential energy, which is half m omega square q square, that also comes out to be En by 2. Okay. So if you add these two up, if you add these two expectations values up, no matter where exactly in P and Q are these system located, it always adds up to be En by 2. It always adds up to En, no matter what.
Okay, sir.
Okay.
Oh, yes, sir.
So there is no conflict with the uncertainty principle here. Okay.
Sir?
Yes.
So I have two questions. Like one is that if we say that like for so if we are looking at the point where the graph is intersecting the QT axis,
Yes.
QT. So here it is like the P and the corresponding momentum is zero. So like
I'm not saying that the particle is at qt equals 0. I'm saying that the particle can be anywhere on that ellipse, but it has to lie on the ellipse. So the ellipse has infinite number of points.
points, yes, sir. So it means like it can possibly be at that point, right? Where the momentum
Yes,
is.
but you do not know for sure. That is the point.
Okay, sir. And so other thing that the volume of which we get of this ellipse is this 2e by omega. So it's basically of the same dimensions as the edge. So does it have any like
No, it
significant?
is the dimension of angular momentum.
Okay, okay, sir.
Okay. So it's basically p times q, that's angular momentum. I mean, in the traditional sense, not always, but in this case, it is angular momentum.
So
All right.
I just looked at this e by omega, so I thought that it is like h cut dimensions. It has.
Yeah, h cut is angular momentum.
Okay, sir.
Okay, so the Planck's constant is basically angular momentum. In fact, that was the Bohr's hypothesis. Bohr said that the angular momentum was quantized in his original hypothesis.
Yes, sir. Can I just ask this question along this tangent? Like, so we always say that the Bohr said like it is quantized. So how did he came to that like conclusion?
Oh, that was a desperate attempt. Let me finish this, then I will talk about that. Okay. I do not mind talking about that, but let me finish this first. Okay. So after
Okay.
that, let me just two more lines. Let me write, and then I will come to that. Okay.
Okay, sir.
So, all right. So this is volume in between two consecutive energy levels is VEn plus 1 minus VEn. Okay. So the so remember this. So the system can either be on that orange ellipse, or it can be either on this green ellipse. Okay, this is the point of quantum statistics, is that it can never be the space in between. Okay, so it has to always take, I do not know what is happening with this thing today. So it can always take a quantum jump. So whenever it makes a quantum jump from one level to another, so there is a certain region in phase space that is inaccessible to it. Okay, so, and that is the minimum volume of the phase space that a quantum state should occupy. Okay, so so that we take, I mean, uh, usually quantum statistical mechanics, uh, mm, uh, we usually take it at like we have large number of particles and we have macroscopic energies. So we are taking almost at the n very large limit. Sorry, my computer got frozen. All right, so n very large limit, but it will not matter in the end. So, and so this would be given by basically 2 by omega, pi times 2 by omega, En plus 1 minus En. Good. So En plus 1 minus En is basically h cross omega. So this is h cross omega, and you say that the space between these two consecutive energy level is basically h. So now we already know that harmonic oscillator is my minimum uncertainty wave packet. So harmonic oscillator, as long as the uncertainty goes in phase space, uncertainty goes in x and p, harmonic oscillator is the best you can do. Okay, the Gaussian wave packet is the best you can do. Okay. But even in that scenario, the phase space uncertainty, or the space between two consecutive quantum state in phase space, it cannot be reduced any lower than h. Okay, so that's why even though in quantum mechanics your minimum uncertainty is h cross by 2, the minimum volume in phase space that you can have is still h. Okay, so hopefully that clears things a bit, and you might now connect why we take this limit to be h cross by 2 and this limit to be h. So both has to do with the harmonic oscillator problem, and since our harmonic oscillator is the minimum uncertainty, it manifests a bit differently in these two different scenarios. So although in quantum mechanics your delta x delta p is h cross by 2, the minimum phase space volume that a quantum state can assume is h. Okay, now you can ask questions first regarding that, and then I will take the other question about Bohr hypothesis also. Okay, so no further question from this. All right, so now tell me about the other question, what you were asking about quantum mechanics. Let me see if I understand it correctly.
So like when we say that the Bohr quantization, it was just like proposed that the momentum is quantized, right? And also, sir, in this example, we are saying that some region is always like inaccessible. So how is it like possible that if it is at like one point and like in one inner ellipse, and it has to transit to the outer ellipse, or we can say the consecutive ellipse, so like it should always like pass through that region, sir. I mean, from common understanding, I think.
No, if you are trying to understand it intuitively, there is no intuitive understanding of that. First of all, this phase space diagram and the hydrogen atom orbitals are different. The hydrogen atom orbitals are not phase space diagram. Those are real space diagram. Those tells you the probability of finding the system or the particle or the electron in that physical space. This phase space diagram that you are drawing, there is no probability involved here. I am not trying to find the probability of finding the system in that thing. It's not that. Okay, it's not. So the physical space diagram and the phase space diagram are two different things. Okay, so first you must disentangle that. Now, if you are coming to the question of say Bohr hypothesis, like how Bohr gave that hypothesis, is kind of back calculation. Okay, how much time do I have to discuss this? Okay, it's 11:42. Okay, I can perhaps take the rest to discuss this. Now this has to do with the history of quantum mechanics. Now the way the quantum mechanics is perhaps taught in your undergraduate studies, there are certain aspects that are never emphasized. For example, it is always stated that so it starts with wave particle duality. It says that the light sometimes behaves as waves and light sometimes behaves as particle, and you don't know when to apply which. But it is not entirely true. I mean, everything can be. So the quantum mechanics is the thing. It it depends on how you interpret this thing, and it is also kind of becomes ingrained in your mind that the wave interpretation of light is more intuitive than the particle interpretation of light. That is also not true. So once you are dealing with interference, diffraction, things like that, you are perfectly fine that you think things are falling into place, so light must be wave. It behaves like wave. It looks like wave. But the main problem was that propagation of light through vacuum. Okay, so for example, from sun, the light is coming to Earth, and in between that there is entirely vacuum, nothing else. Now light carries energy, because when light falls on your skin, it heats up. It carries energy. Okay, and so how does a wave carry energy through vacuum? Now, if you remember, the interpretation of how wave carries energy is by making the medium particles to oscillate. So when you, like the standard example that is given, you throw a rock into a pond, okay, and the medium particle vibrates, okay, and since the medium particles are interlaced by the force of cohesion, so vibration of one particle makes the adjacent particle to vibrate, and that's how the energy propagates in the form of a wave. So that's why we say that like you have this idea of elastic waves, that it propagates through a medium, and that's how a wave carries energy. Now that then so this explanation doesn't work if you think that from sun to earth, light is essentially propagating through a vacuum and it is carrying energy. Now then you ask, how can a wave carry energy when it's propagating through vacuum? Okay. This for me was a crucial moment, and this is one of the reasons why Newton, as early as in 19th century, who kind of liked to thought light as a particles, because if you think light to be a stream of particles, then this problem doesn't occur. I mean, it's a stream of particles, it can propagate through vacuum. But if you cannot get rid of this wave nature of light, then you propose things like ether. So there must be ether in between. That's why people proposed ether, and that was falsified in Michelson-Morley experiment. Okay. And then came black body radiation, and then Planck did explain it with, again, quantum nature of light. The idea of Bohr came from the hydrogen spectrum. So something in hydrogen atom did not make sense. So so basically what you have is that if you excite a hydrogen atom or many hydrogen atom, now from retrospect that there is this proton and kind of nucleons in that thing. Okay. So now when this starts to jump into this, and a certain frequency of wave is emitted, certain frequency of light is emitted, and you have to explain that. And that's how you have the Lyman series and the Paschen series and the Balmer series. So people know about these hydrogen spectrum before even knowing quantum mechanics. That is the point. Okay. And before this was happening, Planck also said that light actually comes as packets of wave, and those each of the packets are like h nu. So light of a certain frequency comes as a packet of wave. So the minimum wave packet you can have has an energy of h nu. Okay. So then Bohr, what Bohr did, like Bohr was always a radical. Okay. He went against the established things. Okay. By the way, at the same time, there was this Rutherford experiment of atomic structure, and Rutherford also gave the solar model experiment. The solar model idea of atom, that in the center there is a nucleus and the electrons are orbiting around the sun, and that goes into direct conflict. That if a charge is accelerating, like it's going in a circle, so it is accelerating, and then that charge should lose energy and it will fall into the nucleus. Then came Bohr. Okay. Bohr says, I don't know what happens with the electron. Okay. Bohr came, and then it says that I don't know what happens with the electron, but if it moves in these orbits, somehow it does not radiate energy. Bohr didn't give a valid explanation why it doesn't lose energy. Okay. So he said that it doesn't lose energy, and when it falls back to one of the lower states, it emits a light of frequency nu, and the thing is given by h times nu. Now, the Bohr quantization formula that you know about and love, so mvr equals nh by 2 pi. That is the Bohr quantization formula. Okay. So he did that by back calculating. So already people knew about the frequencies of light that should be emitted when you fall from this one to this one. Okay. And Bohr did a semi-classical treatment. The semi-classical treatment you learn in book, that if this is my n equals 1 and this is my n equals 2 and there are higher n orbits, then from a semi-classical treatment you know that the kinetic and average kinetic energy and potential energy, that is to say the total average energy, falls off at 1 by n square. Okay. So even without doing quantum mechanics at all, perhaps all of you have done this exercise, that the average energy, the nth orbit energy, you can obtain it by this semi-classical treatment. Okay. And to this day, we do not understand why this semi-classical treatment works. Like by solving exact quantum mechanics of hydrogen atom, we happen to get the same energy, but that's a happy accident. There is no like underlying meaning why these two results match. Okay. So Bohr knew that En is 1 by n square. Okay. And then he had to replace the V and R. So he had to kind of hypothesize how V and R should be related to this n, such that the emitted frequency matches with the formula that we have. Okay. And then he came out to that this should be the rules such that it matches, agrees with this thing. Okay. So that is how Bohr came to this hypothesis. But the story doesn't end there. So this actually helped us build what is known as today the concept of stationary states. So the stationary, so at that time these were quantum states. The name stationary state came later with de Broglie. So first of all, you should, when you learn about quantum mechanics, first of all you should learn about the history of quantum mechanics. Is fascinating. So there are two aspects of quantum mechanics. So if you are if we are looking of quantum mechanics, then one of the thing is the say quantum nature of light, or rather let me write say particle nature of light. Okay, so wave nature of light is already established. The new concept that came into being is the particle nature of light, assuming light as quanta. Okay, so this is the thing. So for example, so the in support of this there are many calculation and things like, so for example, Planck black body radiation formula. Okay, this is one of these things. Then comes photoelectric effect. Okay. Then come Compton scattering. Say Bohr hypothesis. And I can go on actually. So these are all proof of particle nature of light. So in all these things, the thing that is common is that you are assuming light to be made up of small particles that are composed of these waves called h nu, so the h nu packets. But there is a complementary aspect that is not so much talked about. It's the opposite of this. So this is the wave nature of particles. Okay. So remember, the quantum revolution started with this. People were bothered too much about this, and this was started by Planck, Bohr, Compton, etc. So you know by now that. So this came later with de Broglie. Okay. Now things that are obvious to us, now you take for granted that de Broglie said that P equals h by lambda. Okay. So de Broglie said that this should be my momentum. A particle of momentum P should behave like a wave such that this is this thing it will behave like a wave with wavelength lambda, and you can treat it as a wave. Okay. Now, how did de Broglie arrived at this thing? Okay. Now remember, from this, so these are two different aspects. Particle nature of light does not necessarily imply wave nature of particles. Why should it be? Why should you assume that a cricket ball is moving like a wave sometimes? So now, so de Broglie had an amazing epiphany, I would say. He looked at this Bohr's hypothesis and tried to figure out what is probably contained in this that makes this happen. So he said, he somehow said that, all right, so there is something that does not make this these electrons to radiate and fall into the nucleus eventually, that makes this thing, let's say, somehow stationary. And what is that mechanism? Then he remembered, I don't know how he connected this thing, but this is the amazing part of de Broglie hypothesis. By the way, when de Broglie was giving this hypothesis, it is the time of First World War. You can read about history, and de Broglie was posted in Eiffel Tower looking out for like German forces. Anyway, so he had this idea that if you are talking about a stationary wave, when does a stationary wave survive? So if the kind of the length of this the length that is available perfectly fits a wave, something like that. Okay, it perfectly fits a wave, or something like this. Not so he had this essential idea from this thing. Okay, so if the wave does not fall into place, so if you do not have perfect node at these points, if you have something like this, so these kind of waves will die out. Okay, so these things will die out, and this will survive. This kind of stationary waves will survive. We know that from experience. Okay. Now, so de Broglie said that this Bohr's orbit, which he called stationary orbits, or I think so they are stationary only because the electrons that are moving inside that orbit, they behave as a wave, and the wavelength is such that in this orbit they are able to form a stationary wave. Okay, so what we try to propose is that the length of the orbit is of course 2 pi r, if r is the radius of the orbit, and then that length must be an integral multiple of n times lambda, and that's why those electrons that are moving in that orbit are stable. Okay, and that's why they do not fall apart, and that somehow gives the stability. Okay, so now according to Bohr's hypothesis, you can see that mvr is nh by 2 pi. So if you substitute substitute here the value of r, so it would be given by nh by 2 pi mv. So that is the r from Bohr hypothesis and n lambda, and you see now, voila, so you get that thing, n cancels, and you get h by mv equals lambda. So in his mind, he says that it is possible the Bohr hypothesis works as intended only because the particles that contained in Bohr's orbit, they also behave like a wave with an appropriate wavelength that actually matches this thing. And he said not only particles would behave like, not only waves should behave like particle, or light should behave like particle, the particles should also behave like wave, and that is P equals h by lambda. And that was subsequently confirmed by an experiment called the Davison-Germer experiment. I do not know if you have learned this experiment, but this is a very interesting experiment. So remember, there are two, according to from the history of quantum mechanics, there are two independent aspects. There is the particle nature of light, and there is the wave nature of particle. And then people realize that this should be one single aspect. There should not be like two different manifestations of the same phenomena, and that's what was done by Schrodinger and Heisenberg in independently. Okay, so this says that these two apparently disconnected things basically follow from the same kind of mechanics, which we call and learn to see quantum mechanics. So this is kind of the history of quantum mechanics in a nutshell, if you care about that. And I hope it answers to a degree what Bohr did, what he did, and what kind of information did he have when he was. So, I mean, let me know if there is time. I don't think there is time, but if there are one or two quick questions, I can take it.
Sir,
Yes.
do we have a single experiment which simultaneously proves the dual nature of light? I mean, the particle nature and the wave nature.
I mean, there is no dual nature of light. I mean, there is only one truth in things. Everything behaves quantum mechanically. Okay. I mean, it do not fall into believing that this interference and diffractions are proof of wave nature of light. I mean, interference and diffractions can be explained using quantum mechanics, the quantum nature of light also. And that is the paper I gave you to read, actually. So you read that paper and you will have an idea. And that's what I want you to see, that it's not to explain diffraction, you need to employ wave nature of light. You can explain it very easily using uncertainty principle and particle nature of light. Many book discusses that. So let us grow up, and there is no dual nature of light. It's not light behaves as waves on Sundays and Mondays and the rest of the day is particle. Light behaves as light. The governing mechanism, the governing physics is quantum mechanics. That's it.
Sir, excuse me.
Yes.
So in that paper, they actually like calculated the interference patterns by considering like the direct quantum mechanics. So like, is it always possible for like all the experiments of such scale, because they have not used.
Yes, it is indeed possible to do everything using quantum mechanics, but we know that classical mechanics is an approximation of quantum mechanics. So for the same reason, you do not apply special theory of relativity for particle moving with low velocity. Although in principle it can be reproduced, it would be like killing a mosquito with a hammer, but in principle it can be done.
Okay, sir.
So anything you know can be explained using quantum mechanics, but like sometimes it would be an overkill, or sometimes it would make things insanely difficult, because like solving Schrodinger equation is no trivial thing. Okay, it takes an effort, and that's why you can solve exactly only hydrogen atom. Even if you go to a helium atom system, you cannot solve it exactly anymore. So solving Schrodinger equation is that difficult.
Okay, sir.
So it's not very easy that given an arbitrary potential, you would be able to solve the Schrodinger equation. And that's why you develop technique, approximation technique, that is called perturbation theory, variational principle, WKB approximation. So when you cannot solve Schrodinger equation exactly, what kind of methods would you do adopt? So that is the thing. Quantum mechanics is the theory, but it is not very straightforward to apply it everywhere. And that's why we use approximation.
Okay, sir. Thank you, sir.
Anything else? Okay, so if there is nothing, I will stop recording now.